Hello everyone, my name is Marc and I'm one of the organizers of the MIDOG 2021 MICCAI challenge. Now, as you might know, the challenge target is to detect mitotic figures regardless of the scanner, which is why we call it mitosis domain generalization. In this small video, I want to showcase to you how to set up your Docker container to submit it then to the challenge. We use grandchallenge.org in order to make the whole evaluation process automatic. Now, in order to do that, we provide an example for you, and this example contains a mitosis detection algorithm that can be a prototype or whatever in order for you to learn how to do the submission process, in order for you to learn what is the expected output format, and of course it might also serve you as a template. Before we get started, let me first say that there is some prerequisites and some recommendations. First of all, you will need Docker, an installation of Docker, in order to be able to test your Docker container and to build it to then later on submit it. Secondly, you need the pip package evaluatils from Grand Challenge, which you can just easily get via pip. Then I can only recommend, as also the Grand Challenge guys are doing, if you're using Windows, it might be really helpful to use the Windows subsystem for Linux or WSL, and or of course to go straight ahead and install Linux on your machine. That helps a lot for developing. In order to get you started, we provide an example Docker container. So that is a reference algorithm that you can of course use to learn from, to see how things are set up, how the output is expected to be. And this was provided kindly by my two colleagues, Katharina Breininger and Frauke Wilm from Friedrich-Alexander-Universität. So in this Docker repository that we've set up, you can see it here. It was still private while I recorded this. We can now, just go ahead and clone this. So let me just get my mouse pointer to the right position. Okay. And let's take this URL, copy, and just then clone this using git. So git clone and then paste the URL. Okay. Now I have to log in while, as I said, this repository is still private while recording. You will not have to when this is out in the wild. Okay, now let's go ahead. This whole repository was cloned now, and I can go into the directory and let's just get an overview using Visual Studio Code. Here you can see that we have first of all, a couple of scripts, which is build.bat, build.sh, export.bat, export.sh. So there's always a batch file for Windows and there's a shell script for Linux. So you can, of course, use everything also in Windows using the batch files. And you can also, if you're using a Windows subsystem for Linux or a Linux machine, then you can just conveniently run the shell scripts. Okay, I don't want to know about updates now, and let's just get straight to it. So there's two files that are of importance here. The first file is this file process.py. Process.py is the main file. The main file that is the one that will run the whole process. This is run from the scripts that evaluate the Docker container. Then there is the detection.py file in our example. This file sets up the complete model. It loads the model weights and sets it up that it can then process images and also does the whole post-processing, non-maximal suppression, etc. So here we have a class called MyMitosisDetection, and we have a couple of parameters. So if you're using, like we're doing here, a RetinaNet-based approach, then you know that it will require some anchors, and the anchors have scales and ratios and sizes. So for that, we have some parameters here. Then we have here the class, which is in a subdirectory. So it's in the subdirectory model. It's in here, which we don't look at now. And here, this is being instantiated here. So Then let's go further on. So the model is loaded here from a file that is given by the other process.py. And then we have the main function, which is the function process image. And the process image function sets the model into evaluation mode, and it will then go through each of the patches and run the model. Now in our case, we used a RetinaNet with a patch size of 512 times 512. And in this case, this function knows it, and it will make sure that only, that only patches that are part of the image are fed through the network. Now, first of all, we do here a queuing of image coordinates that we then later on will process. So this is the queuing here. Then moving on, we do here the main loop, which gets one batch. So depending on the batch size, of course, I think here it's 8 or 10. So here we get one batch of images, and we will just run the model on those images and then do a post-processing of those. Now, I don't go into details about the get batch function. I think this is more or less self-explanatory, and also the post-processing, which is somehow related also to the RetinaNet approach. The bottom line is that we will get here some kinds of coordinates, which are the boxes. So the RetinaNet predicts bounding boxes. So here we get the bounding boxes as image coordinates. So depending on the offsets, which are here in this X real and Y real, and the coordinates within the patch, we will then get this list that we here extend by cur patch boxes.append, and we return this. Yeah. Finally, this is then, so this whole process image function is run for each image, and image is here, as you can maybe also see by this .shape property, this image is a NumPy array. Of course, now there's the question, where does this NumPy array come from? So let's go into that briefly. So here, for example, we have the, here we have the process file, and how does it work? So first of all, let's see how it is being run. So if name is main, so in this case, the file is run not as a class, but on its own, then we do the processing, and the processing will then do this method predict. So process is also a method that is provided by the eval-utils, and it runs the predict function on each of the input images, which are simple ITK images. From these images, we get then the NumPy array, and then we run the process image function from the detection.py file on each of them. We do a final non-maximum suppression on these or on this here, because non-maximum suppression you have to do finally on the image where you have all the patches or the detections from the patches together. So this is the final non-maximum suppression here. And then we do the generation of the return array, or in this case it's a dictionary. So here we have the candidates, the candidate scores, and we calculate these here as their center coordinates. So this is x1 plus x2, which are the left and right coordinates of the bounding box divided by 2. So it's the center of the bounding box. And here we have the same thing with the y coordinates. Yeah, finally, we generate this dictionary result. That is what is being expected from the Grand Challenge servers. Okay, so that's basically how it is set up. And of course, you can now use this as a template, as an example, to run your own models to then be able to submit your containers. Now, how should you then proceed when doing this? Okay, first of all, of course, you can just say, let's build the container. Now we can build the container to see if everything is set up properly. Let's do that. Not sure if we need sudo here. Let's see. No, we don't. We need sudo. Okay. So then let's run sudo on that. And then you see that the Docker image is being built. So now it built the Docker container. And now we can run the next script, which is the test script. So the test script will also build the same Docker container. So just in case that you are certain that the build works out great, then just go ahead and take the test script. So we run that, and yeah, here you can see now that it is being run on the test image that we provided, and here we have some example outputs. So this is the JSON structure that is outputted by our Docker container, and this is being checked against a reference structure, and the reference structure is also provided here, and it is in the test expected output.json. Here you can see that this is the reference structure. So if all goes well, then we get a test successfully passed, and then we can export the container to then go to Grand Challenge to submit it there. In order to do that, we run not build, but export.sh, and that takes also a little while. And if it's done, then it creates a .tar.gz file, which is an archive, and which we then can upload to Grand Challenge.